All right, in today's lesson, we're going to review an IB eye-level assessment prompt with systems of planar equations. So essentially, we have a 3 by 3 system here. Of course, the twist is two of the coefficients are unknown relative to each other. So we have to see, then when we read the question, we see that basically there are conditions for alpha and beta such that the system would have none, one, or infinite solutions. And so we have to really understand the nature of solutions to planar systems before we could actually even answer the question. But essentially, understanding the system has no solutions means 3 planes will never intersect at a singular point. One solution means all 3 planes will intersect at a single point, and here this means the 3 planes will intersect in a line. So what we have to do is figure out a way to answer the question. Now, usually when it comes to finding solutions to 3 by 3 systems, we have to use either row elimination or we have to use the determinant and or the discriminant, sorry. And the discriminant in this case would be sort of a way to get around it, but it would involve a lot of thinking because the discriminant does not include this beta. So I'm going to go strictly to the old row operations for elimination of variables. So essentially what I want to do here is I want to eliminate the x variable first. And notice my notation, I defined each equation as a row. And I say if I take -2 times row 1 and add that to row 2, so basically what I'm going to do is I'm going to create a fourth equation, which would be the result of this algebra right here. So that produces, we have the 4 times the first equation plus the second equation gives us y plus 2z equals 4. So keep in mind, I knew that if I multiply this by -2 and add it to that the x's will be eliminated, which was the goal. So now I'm going to eliminate this x from the third equation, and I'm going to use the first equation to do so. So that gives me the opposite of r1 plus r3. That's the opposite of r1, that's plus r3, and we get that result. Now, with the equations that are left, now we have a 2-variable system. Let's get rid of the y next. So to eliminate the y, I'm going to take the equation 1, multiply it by 3, add it to equation 2, and as you can see, we end up with just an expression for z. So this is the truth of the matter. The solution to this system is alpha minus 2 times z equals beta. Now understand that if I knew alpha and beta, then I know the value of z. And if I know the value of z, I could use this equation to find y. And if I know y and z, I can use any equation to find the x variable. Thus I have the solutions. So basically, then we understand that if we could solve this equation for z, we just divide both sides by alpha minus 2, I can see that the solution for the value of z would be beta over alpha minus 2. And that's cool unless, here's the money, unless alpha is 2 and b is not 0. Why does that matter? Well, that would mean that 0 times z is equal to beta, which is just untrue. If beta is not 0, we take 0 times z is going to be 0. We have an untrue statement, hence there will be no solutions to the system. And that's for all values of z. Now, in order to get one solution, we need alpha to not be 2, but then beta can be anything you want. Because that's the situation where we divide both sides by alpha minus 2, and we can see that beta can be anything, including 0, and alpha could be anything except 2, so that we don't have to divide by 0. That would be the value for z, and then we go back and find y and x like I mentioned earlier. So the one solution conditions are alpha is 2 and b can be anything. Finally, to get infinite solutions, we need alpha to be 2 and beta to be 0. Because there, we're going to zero out the z variable, but we're also going to set it equal to 0, which is a true statement, and it's true for all values of z. Any number of z I can think of, I'm going to have a true statement in the third set. So, I hope that makes sense. Now, the rest of the question was, if for the situation where there are infinite solutions, tell me what they are. So, we're going to take the conditions where alpha is 2 and beta equals 0, for example. and that is the system that's created. So the third equation in the system is just going to be 2x minus 2y equals negative 12. So there is no z there. So let's see that. Anyway, to get the remaining solutions, recall that all we have to do is let z equal t, or lambda, or some parameter. Now, the reason I wrote down these two equations here is because if z is equal to t, I could put t in for z here and solve for y, or I could put t in for z here, and of course I would also put in my alpha 2 and my beta 0, and verify that when z equals t, that we get the same number. So that's why I put a little double check here, but in the interest of time, I'm going to continue on here. When z is equal to t, I replace z with t and solve for y, and then I go back to this equation, and I get my x, y, and z. So this is something that we've done before, so I'm kind of like going quickly over it. But remember, basically what we do is we say, all right, let's let z be the parameter time, and then we work backwards, just as if time is an actual number like 5 or 6 or 7, and we work backwards to find out what y is, and then when y and z are, we work backwards to find out what x is. So that's what I did right here. So the first thing I found out is when z equals t, y equals 4 minus 2t. So then I went back to the original first equation, and now I have x, and then a bunch of expressions with t. So now I have x in terms of t, y in terms of t, and z in terms of t. Now this produces the vector equation of the line shown here. Remember the starting position and the direction vector. But also remember that the instructions were asking for the Cartesian equation, not the vector equation. So to do that, I'm going to solve each of these for t, and they're all going to be equal because they're all based on time, and then I could set them equal to each other. So that's where we get the Cartesian form right here. Notice I didn't do any messing around with simplifying. I mean, here's negative, negative, negative. I've seen in the solutions keys for IB exams, they don't really care. So best avoid those kinds of silly mistakes that come with simplifying, and write the equation exactly the way you see it when you solve directly for the variable t. I hope that's helpful. Thank you.